I'm Karthik. I'm a principal engineer and scientist at NVIDIA, engineering lead for the Earth-2 initiative, which aims to build digital twins of weather and climate. And I'll dive right into it. Hopefully you can hear me fine and see the screen.
Yes.
Okay, great. Thank you. So the context is clear. The future is going to be harsh, and we need to prepare for it, and we need a whole range of tools to deal with the potential consequences of climate change. High-resolution climate prediction is a serious computational challenge. This is adapted from Tapio Schneider, Chris Bretherton et al. In Nature Climate Change a few years ago. The compute demands for computational modeling of climate is obviously exponential, and we see that if we want to go towards 1 kilometer at 20-second time steps, we need something like 30,000 times the baseline, which is currently 25 kilometers at 10 minutes. And at 100-meter resolution, to resolve these low clouds that are responsible for large uncertainties in climate projections, we need something like 500 million X compute. And with current compute growth, the projections are that we would only be able to do this in 2060 or so, which might be too late. So we need alternatives to work with that hard challenge. This is a slide drawn from Bjorn Stevens' keynote at the GTC a few months ago. Even if we can compute these very expensive trajectories, let's say 1 kilometer or sub 1 kilometer scale predictions for hundreds of years, it's almost impossible to extract the information content, let alone interact with this data, because we're talking about potentially hundreds of petabytes to an exabyte of data. So we need tools that can help us interact with the data at low latency. So advances in HPC and machine learning are offering a great promise. Of course, we've been doing HPC for a long time, but accelerated computing at data center scale, along with machine learning, can potentially give us something like 1 million X speed up. We're not quite there yet, but I'll show you some results that are promising in terms of several orders of magnitude speed up compared to traditional numerical methods. So Earth-2 began as a vision, very much inspired by Destiny, which I'm sure we've heard about today. And there's many of you in this room that are actively working on it. So the goal is to create a highly interactive climate information system that can serve society with next generation climate predictions. Both of these images are from the papers on Destiny, Peter Bauer, Dubin, Stevens, and several others. And the idea is that we want to have these systems that we can ask these what-if scenario questions and receive answers in a reasonable amount of time. So you imagine you could select a region of the planet. It could be an entire continent or a state or a city, or maybe even a specific part. In this case, we're looking at the US, California, the Bay Area, San Francisco, and then a particular part of San Francisco. And you want to ask questions about climate change's impacts on food, health, agriculture, energy systems, and various other applications. So the first mission of Earth-2 is that we want to be able to receive useful visual and statistical guidance when we ask these questions from a highly interactive system at high resolution that can serve society. So that's goal number one. But we also want to be able to receive these responses in computational fidelity and ambition. And by that, I mean that we want to be able to have responses coming from reliable and credible high resolution climate predictions that seem impossible today. So the only way to achieve that is to really combine physics with machine learning and HPC to achieve these computations that are credible and have high fidelity and are at resolutions that are potentially kilometer or sub-kilometer scale. So how is NVIDIA going to make a difference here? And of course, this is not a problem that we're the only ones solving. There's many others, obviously Destiny, but several other digital twin projects are already underway across the globe. So we're complementing all of that work. So we think that with the following technologies, which are listed here, we can make a difference. And this is meant to be very much collaborative with all the other efforts that are going on across the globe. The first is Omniverse. I won't spend much time on it. We could spend an entire separate talk on Omniverse, but I'll just have 1 or 2 slides describing that. The focus of this talk will be on machine learning. So that's the second bucket here. We have platforms, of course, at NVIDIA for developing various types of machine learning models, including physics-informed machine learning models. The third, which has sort of been our workhorse for a long time, is GPU acceleration of various weather and climate codes, and we will continue to do that, including for storm resolving models. The fourth is Nucleus, which I'll mention briefly about. It's essentially a hub that brings together various different types of data sources along with computations and visualization capabilities, and finally, of course, exascale compute, including the OBX SuperPod and various other types of chips, including the Grace Hopper. So what is Omniverse? This is just my one slide description of Omniverse. We could have a whole talk on this, but very briefly, it's meant to be this platform that enables scientists to create digital twins together. And this is, of course, a cartoon representation. We don't have all of these pieces put together just yet. The nucleus is the sort of hub of the Omniverse platform, where we bring together models. For example, on the top left is icon. Bring together data. For example, on the top right are some images of NASA satellites, AI models of different kinds, archives of data, potentially petabytes of data coming in from things like the CMIP6 and various other data sets, analytics tools, including things that exist in the community like Pangeo, but also custom analytics tools, and then finally, various types of impact models and downstream models that customers and users care about. So the idea is to have an interface where you can have all of these interacting together and very fast transfer of data and information across these different pipes. So Earth-2, as I mentioned, is a highly collaborative project, and the goal for us is to be able to build the technologies in sync and in collaboration with the deep scientific expertise in academia and government, and also to work with other companies and industries that are embarking on this project. So our visualization engineering, AI, and full stack expertise is meant to complement all the other expertise that exists across the community. Okay, so that's my hopefully not too fast introduction to Earth-2, and now I'd like to dive into some of our early machine learning results in particularly on working with machine learning predictions for weather, and also maybe some teasers on extending towards climate. So we began exploring data-driven weather prediction. Of course, Peter Dubin and Peter Bauer and several others have been doing this for a long time. We started off with ForecastNet, our model, which was developed over about a year ago, actually less than a year ago. And these are some characteristics of this model, ForecastNet. It's meant to be medium-range weather forecasting. We're exploring subseasonal to seasonal at this point, and potentially beyond that. The type is a full model emulation, so we're emulating the entire data set, in this case, ERA5. So the whole atmospheric dynamics is emulated as a single model, as against other types of approaches that are hybrid, where you emulate certain processes like convection or radiation or other characteristics. So this is a full model emulation. The architecture is an adaptive Fourier neural operator, which I'll describe a little more in a couple of minutes. It's at the ERA5 resolution, 25 kilometer, I guess 30 kilometers. The training data, as I mentioned, ERA5. One of the nice properties of this model is that it can be initialized with not just the ERA5 initial conditions, but also with GFS and UFS. So this is what we call zero-shot transfer learning, where you can have a model that can generalize to slightly different data sets. Of course, we haven't tested this on vastly different data, but that's something that we're working on right now. The inference is extremely fast. It's 0.25 seconds on a single A100 GPU, which means that we can generate these large ensemble forecasts in a few seconds on a single node, which corresponds to a speed up that's 4 to 5 orders of magnitude compared to traditional numerical weather predictions, and also corresponds to a power savings of 4 orders of magnitude. And both of those, the speed up and the power savings, have huge implications, which I'll get to in a second. So this is ForecastNet, and the one slide description of, I guess, the history of data-driven numerical weather prediction, starting off with Dubin and Bauer in 2018 at 6-degree resolution, 1.8K pixels. The community has had increasing resolution over time, 2K pixels, 2.6K, 16K, the chi-square graph neural networks at 64K, and ForecastNet right now is at 1 megapixel, 0.25 degrees. So clearly, there's been a very rapid increase in resolution in our capabilities to ingest and extract useful information from large data sets. And the goal is, of course, to push to higher resolutions, and we're excited to probably go down to 10 kilometers next, and then one day, 1 kilometer resolution as well. So how are we able to ingest these large amounts of data and extract useful information? Well, it does need large AI models. And in this case, we're using a novel transformer architecture, which combines transformers with Fourier neural operator blocks. I wouldn't get into the full details, but very briefly, the idea is to do mixing in the mixing in the spectral space. So we're using the convolutional operator here. Here's Fourier transforms, and we're doing essentially what a standard neural network would do with the actual physical inputs in spectral space, and we then take an inverse Fourier transform. And this is very effective at learning essentially global correlations, global convolutions. So things that matter over long spatial and temporal ranges are included. So it's very good for multi-scale systems and for solving nonlinear PDEs that we care about in fluid dynamics. On the right is a schematic of the architecture. The key part is that this is a transformer, and the spatial mixing layer of the transformer is done using the Fourier neural operator with the FFTs and the inverse FFTs here. Without getting into too much more detail, this is much more efficient than a traditional transformer architecture, partly because of the FFT, but also because of various other features which are described in the paper, including weight sharing and block diagonal mixing and so on. So what are the characteristics of ForecastNet? And this is constantly changing as we evolve, because every month or two we upgrade the model. But in February 2022, a few months ago, we were training on 20 variables from Arrow-5, and by variable I mean a single physical variable at a single vertical level. So velocity at 3 different levels would mean 3 different variables or channels. So we had surface variables, velocities, temperature, pressure, and also precipitation. We have U, V, and Z and temperature at 4 different levels. We've also included relative humidity and integrated water vapor. Since then, we've added a few more levels to this set, and so we now have a slightly larger set of variables. But we're expanding towards hopefully one day being able to ingest the entire data set, the full 3D state vector. It's trained on Arrow-5 from 1979 to 2015. The validation is 2016 and 17, and the test is 2018 onwards. I see I have probably about 7 or 8 minutes. So I'm gonna skip some of the details of the architecture and dive into the results. The paper has a full description of how the model was trained. The computational performance, as I mentioned, is key to the benefits of this model, and I'll also describe the scientific fidelity of the model in a moment. But as a reminder, it's 4 to 5 orders of magnitude speed up over NWP, which allows us to create these grand ensembles, which we have now calibrated, which I'll tell you in a sec, and 4 orders of magnitude smaller energy footprint. We've also taken the model and scaled it out on large machines in an attempt to win the Gordon Bell Prize, which unfortunately we did not win, but it was still a very exciting exercise. This is results for scaling this out to Jules Booster, Perlmutter, and Selene 4100 GPUs. We have very good scaling efficiency using various different approaches, including model and data parallelism and several other performance optimizations. We achieve a peak performance of about 150 petaflops, and this reduces the solution time to about 60 minutes. So our scale has been increasing since we started as we keep including atmospheric variables. I'm showing just one or two examples here. In the interest of time, the takeaway is that as we increase the amount of training data and the different atmospheric variables that we use, we're starting to approach IFS's ACC skill score, and we've reduced the gap between our model previously to the current latest version by almost half for Z500 and more than 80% improvement on surface winds, and we hope that one day we would match IFS. We don't know, but we'll find out. There's excellent skill on various different variables, surface winds, precipitation, several other variables. The details are in the paper. Here where I'm just showing a couple of different types of extremes. Here we have a typhoon in the South China Sea that was captured very nicely by ForecastNet, and also the same in the Atlantic, a series of hurricanes. We've done this analysis for atmospheric rivers, extratropical cyclones, and other types of events as well. Calibration of our ensembles was one of the first questions that Peter Dubin raised when he read the paper, and a very pertinent one. And since then, so since February, we've been working on trying to calibrate our ensembles better, using some principled initial condition uncertainty, drawing on lessons from the NWP world. So in particular, using color noise that has spatial correlations, and also a principled model uncertainty estimation approach using Bayesian stochastic weighted averaging. And now we have a good, we think at least close to a good calibrated model in terms of the spread skill match over different forecast days, and also getting closer to the IFS, RMSE, and spread. We've also looked into the CRPS with comparing against IFS, and of course improving the initial condition uncertainty characterization and the model uncertainty, and the spread scale score results in also improvements in CRPS, as we see here. So leading off of the last talk, I can't resist the temptation to reveal some early results on generative modeling to improve our forecasts for the same reasons that were pointed out by Lucy, which is that we have these blurring out of results from typical machine learning models trained on MSE, L1 or L2 losses. And that's because the model is trying to learn the average as against the individual tails of the distribution. So by including an adversarial loss, much like in a GAN, we're able to sharpen and get much better predictions on the fine scale details. And on the right is the ground truth. This is work in collaboration with Berkeley Lab and NERSC. And what is the implication of this work? Well, we do improve the statistics of our extremes. And here we're looking at percentiles on a log scale for precipitation. And we see that with just the standard L1 loss, we have we underpredict extremes, and it gets worse as you get to the further out into the tail of the distribution. In blue is IFS, and in black is R5. If we include the adversarial loss, as has been done in many other GAN approaches and other generative modeling approaches, we see a significant improvement in the tails of the distribution, and we're getting much closer to the ground truth, and this is very promising. And we're testing if this holds out on longer rollouts of the model. This is at 18 hours. We've also, as I mentioned, tried initializing the model with different data sources. This is really exciting and important, especially because we don't have access to real-time initial conditions from ECMWF and Aero5, but from NOAA, we get initial conditions from GFS about 6 hours delayed. So we basically have near real-time initialization using the GFS data. Of course, our model is not trained on GFS, it's only trained on Aero5. But we see that with no retraining, so simply applying the model as is with a different set of initial conditions, we get a skill curve, an ACC curve that's pretty close to what we had with Aero5. And this is promising because this basically implies that the model has learned something useful about the atmospheric dynamics and not just correlations in the data. And this gives us confidence that we could apply this potentially for a wider range of applications that we're exploring. This also means that we can provide real-time forecasts or near real-time forecasts, and so we're exploring, we're sort of looking at our forecasts and other operational forecasts and trying to see how good or bad they are, and look into exciting places where we outperform existing models or we underperform as well. All of this is open source, and in fact, everything that we intend to do with Earth-2 is meant to be open source because it is highly collaborative. So I really invite you to explore ForecastNet. It's on GitHub. The link is at the bottom. We'd love to work with you on pushing the frontiers of this model, taking the model, adapting it for various other applications, maybe regionalizing it, adding downscaling sort of post-processing heads on top of it, changing the architecture, et cetera. Essentially anything you would like to do and modify. We'd love to do this with you if you'd like to collaborate with us, or of course you could do it by yourselves as well. But we look forward to hearing your explorations with ForecastNet. So in summary, we've expanded ForecastNet over the last 6 months very rapidly. We keep including more fractions of the petabyte scale Aero5 dataset, and we keep seeing improvements in the skill. We've scaled it out to large machines, 4,000 GPUs on 3 different supercomputing systems. We've improved the ensemble spread calibration using some principled approaches for initial and model uncertainty. We've done near real-time initialization and tested zero-shot scale transfer of the model, and it's quite successful. We're looking into generative approaches in collaboration with several others, trying to improve extremes and also looking at the fidelity over longer rollouts. I did not mention much about our stability of the model, but we're currently exploring also stability out to sub-seasonal to seasonal scales. And there's some very promising avenues there. Maybe the next time I talk about this, I'll have some results to show. Everything is open sourced, and we would love to work with you in collaboration. So I will probably spend one more minute on just giving a little bit of a teaser about our climate work, which unfortunately I won't have much time to describe in detail. And also this is an area that Mike Pritchard, who has recently joined us, and we're super excited about this, professor from UC Irvine that many of you might know, and he's leading our climate research group at NVIDIA, and he's building up a strategy for expanding out towards various types of climate predictions as well. So as I mentioned earlier on, that this is again drawing on Bjorn Stevens's keynote at the GTC. When you have these very high resolution trajectories at, say, kilometer scale, it's almost impossible to interact with the data. So one approach that Bjorn Stevens proposed was, what if we checkpoint these very large simulations quite infrequently? So we only have checkpoints, say, once every month or so, and then use a model like forecast to essentially fill in between the checkpoints. This would be extremely useful, first of all, for reducing, basically compressing the data output by 2 to 3 orders of magnitude, but also potentially exploring perturbations around those checkpoints. So if we have a conditional model, we could potentially explore slightly different scenarios from just this particular trajectory. So the first step is, of course, to do a good interpolation and then potentially also a little bit of extrapolation around those trajectories. So that's one of the ways in which we're looking at ForecastNet being applied to climate simulations. So we're starting off by trying to do this at lower resolution because, of course, it's faster to train and explore some of these basic questions on the research side. So the first goal is to do this with CMIP6. And then, of course, we want to eventually move to much higher fidelity data sets at kilometer scale or tending towards kilometer scale. And we're excited.
We're running out of time a little bit.
Okay, all right, thank you. I will conclude in a second. So this is my final slide. Looking ahead, we have emulation for CMIP6, tethering to very high resolution data, for example, ICON and IFS at 1 kilometer. Hardware software co-design, I didn't mention much about this, but we're building a supercomputer Earth-2 for this work. We're exploring some coarse grading strategies and various other exciting hybrid machine learning strategies. We have some downscaling approaches in the pipeline. And finally, maybe further out into the future, auto calibration with reinforcement learning to automatically calibrate these large models. Okay, apologies for a huge core dump there, but hopefully that was interesting. Thank you.